At 3 o'clock UTC on May 16, 2026, a correlating interaction region, a compressed wall of charged plasma born where fast solar wind overtakes slower solar wind shed earlier in the sun's rotation cycle, struck Earth's magnetosphere with enough force to push the KP index to geomagnetic storm level G2, the threshold, at which NOAA's Space Weather Prediction Center formally warns high-latitude power systems of voltage alarms, transformer stress, and the potential for long-duration damage. The solar wind that drove this impact originated from a transequatorial coronal hole, a breach in the sun's magnetic atmosphere so large it spans both the northern and southern solar hemispheres simultaneously, crossing the solar equator, a class of coronal hole that space weather researchers classify as among the most potent drivers of sustained geomagnetic disturbance at Earth. The wind it produced reached measured speeds exceeding 700 km per second at the L1 monitoring point, the gravitational balance point between the Sun and Earth, where instruments give forecasters approximately 15 to 60 minutes of warning before conditions reach our planet, 700 km per second. That is 435 miles every single second. That is the speed of what is pressing against the boundary of the only magnetic shield standing between human civilization and the raw electromagnetic force of a middle-aged star. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This kind of reporting, anchored in NOAA, NASA, and peer-reviewed science, depends entirely on the audience that values it. That audience is the reason this work continues. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the Space Weather Archive at spaceweather.com, peer-reviewed research published in Space Weather Journal, and the North American Electric Reliability Corporation's historical event records. Official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently. Through the official channels listed in this video's description, the sources are public, the data is accessible, the responsibility to check belongs to all of us, but that is not even the complete picture. And here is where this account becomes genuinely significant, because what is striking Earth's magnetic field today is not simply a beautiful atmospheric light show for stargazers in New York and Wisconsin. What is happening on May 16, 2026 is a real-time demonstration of a vulnerability that has already in documented history taken a modern industrial nation completely offline. It is a demonstration of how a gap in the sun's outer atmosphere, invisible to the naked eye, detectable only through satellite imagery and extreme ultraviolet wavelengths, can, through a chain of physics that requires no catastrophic solar event at all, begin to stress the very infrastructure that keeps hospitals running, that keeps communications satellites holding their orbital positions, that keeps the power flowing through the lines your city depends upon every hour of every day. The event occurring right now is classified as G2, the second rung on NOAA's 5-tier geomagnetic storm scale. It is not the worst the sun can produce. It is not even close to the worst. But that graduation, the fact that today's storm sits at level 2 of 5, is not reassurance. It is context, and the context is this. Every G5 event in recorded history began at G1. Every catastrophic geomagnetic storm that has ever shut down power infrastructure began with conditions that looked, early on, like the conditions the instruments are measuring right now. The coronal hole responsible for today's storm was first identified in NOAA's GOES-19 satellite imagery on May 13, 2026, when it rotated into what space weather scientists call a geoeffective position, meaning it was aimed directly at Earth. The description circulating among forecasters was specific. This was no ordinary coronal hole. It was classified as transequatorial, stretching from the sun's northern hemisphere all the way through the solar equator and into the southern hemisphere. The significance of that geometry is not aesthetic. Coronal holes that span the solar equator produce fast solar wind streams that hit Earth's magnetosphere across a wider magnetic profile than polar coronal holes do. The geoeffectiveness, the actual capacity to disturb Earth's magnetic field, is measurably higher. The peer-reviewed literature on coronal hole morphology confirms that equatorial and transequatorial coronal holes produce consistently higher KP readings at Earth than their high-latitude equivalents of similar area. NOAA forecasters identified this, issued the G2 watch on May 14th, and the storm arrived precisely within the predicted window. Storm onset, 3 o'clock UTC, May 16, 2026, peak, forecast between 3 o'clock and 6 o'clock UTC. That is the window in which instruments recorded maximum geomagnetic disturbance. The KP index, the Planetary Geomagnetic Activity Index that runs from 0 to 9, with G2 storm conditions beginning at KP6, climbed into that confirmed storm range and held there during peak impact. What the official data actually shows is that G2 conditions carry 4 categories of documented, confirmed infrastructure impact. First, power systems. At high latitudes, voltage alarms begin triggering in high-voltage transmission infrastructure. Transformer cores begin experiencing saturation from geomagnetically induced currents. The slow, powerful DC-like currents that flow through the Earth's conducting crust and find their way into long metal conductors, including the power lines that run across countries and continents. These currents are not fast. They are not the rapid oscillations that powerline engineers designed their systems to handle. They are massive, low-frequency electric flows that transformers were never built to absorb. Second, high-frequency radio communications. On the sunlit side of Earth, HF radio, the communication band used by maritime operators, by remote Communities, by transpolar aviation routes linking North America to Asia experiences degradation. This is not theoretical. NOAA documents it for every G2 event. Occasional complete loss of radio contact is listed as a G2 level outcome on the official NOAA geomagnetic storm scale. Third, satellite operations. The Watchers News Service, citing Space Weather Prediction Center data for this specific event, notes that spacecraft face orientation irregularities as magnetometer readings fluctuate, and that low Earth orbit satellites face increased atmospheric drag as the upper atmosphere expands slightly under geomagnetic heating. Or constellation operators SpaceX's Starlink, OneWeb. This means burning finite thruster propellant to maintain orbital altitude, slowly reducing satellite service lifespans. Fourth, navigation. Low-frequency navigation signals experience degradation for brief intervals. GPS-dependent systems, precision agriculture, aircraft. Instrument approaches, shipping navigation face intervals of reduced accuracy. These are the G2 effects. They are real. They are happening today. And they must be understood not in isolation but in relationship to what the instruments showed in the hours and days before this storm arrived, because the system is not inactive, it is accumulating. On May 10, 2026, active solar region 4436 produced an M5, 8 class solar flare, a moderately strong eruption, and launched a coronal mass ejection that delivered a glancing blow to Earth's magnetosphere in the days that followed. The IMF, the interplanetary magnetic field threading the solar wind between the Sun and Earth, was already shifting and disturbed before today's coronal hole high-speed stream arrived. The B's component, the critical north-south orientation of the interplanetary magnetic field, had been oscillating between northward and southward. During the preceding days, according to observations reported by EarthSky's Space Weather Team on May 14th, when B swings south and holds south, Earth's magnetosphere opens to solar wind penetration the way a door opens when you turn the handle. The longer it holds south, the deeper the penetration, the stronger the storm. Today's CIR impact brought exactly that. Southward B's, elevated solar wind density, and wind speeds in excess of 700 km per second pressing against the magnetopause, the outer boundary of Earth's magnetic shield. Now consider the people living under that boundary. Consider Churchill, Manitoba, in northern Canada, a community of approximately 900 people situated at roughly 59 degrees north latitude, well within what NOAA classifies as the high latitude zone where G2 effects on power infrastructure are most acute. Churchill does not have a road connecting it to the southern Canadian highway system. It is serviced by a single rail line and by air. Its electrical power comes through infrastructure that traverses hundreds of kilometers of Canadian Shield, the ancient Precambrian igneous rock that underlies much of northern Canada. And this detail about the rock is not incidental. Precambrian igneous rock is electrically resistive in a specific, deeply consequential way. When geomagnetically induced currents flow through the Earth during a storm, they seek the path of least resistance, in areas underlaid by ancient, electrically inefficient crystalline rock. Those currents are forced up into whatever conducting infrastructure sits on the surface: power lines, pipelines, telecommunication cables. The rock beneath Churchill, beneath northern Quebec, beneath large portions of Scandinavia and the northern United States, makes those regions dramatically more susceptible to geomagnetically induced current damage than regions underlaid by more conductive sedimentary geology. If someone in Churchill asked right now what this storm means for them, the honest answer is that their grid, their communications, their heating in a community that averages minus 27 degrees Celsius in winter, all depend on infrastructure whose geological substrate was identified decades ago as a primary risk factor for space weather damage. And here is where the historical record descends on the present with full weight. On March 13, 1989, a severe geomagnetic storm, the largest magnetic storm of the space age, as Dr. David Bottler of the Space Weather Group at Natural Resources Canada has formally characterized it, struck Earth. The storm had been preceded by 2 coronal mass ejections, the first associated with an X4, 5 class solar flare on March 10th, the second linked to an M7, 3 flare on March 12th, the second interplanetary. CME shock arrived at Earth traveling at an estimated 1,320 km per second, nearly twice the speed of the solar wind striking Earth today. The storm's sudden commencement the moment the shockwave hit occurred at 1:27 UTC on March 13th at 2:44 a.m. local time, the hydro power transmission system began to fail. Within 90 seconds, roughly the time it takes to read this paragraph, the entire James Bay network went offline. 6 million people across the Canadian province of Quebec lost electricity. They lost it not for 90 minutes or 9 minutes, they lost it for 9 hours. Millions woke to cold homes. The Montreal Metro did not operate during the morning rush hour. Dorval Airport was shut down. Schools were closed. The currents that caused this were geomagnetically induced currents, the same category of currents that G2 storms begin to generate, flowing through the Precambrian shield beneath Quebec, finding the path of least resistance through hydro. As high-voltage transmission lines, saturating transformer cores, triggering protective relays, and collapsing the grid in a cascade that took less time to begin than most people take to pour a cup of coffee. The research paper by Dr. D. Bottler, published in Space Weather Journal in 2019, reconstructed the timeline of that event with modern analytical tools and confirmed that the hydro Blackout occurred early in the storm before the DST index, the measure of the storm's main phase intensity, had even reached its peak. The system did not fail at maximum storm intensity. It failed on the way up. That is not a footnote. That is the warning. The question is not whether geomagnetic storms can take down modern power infrastructure. The question is when. And the additional question, the one that space weather researchers have been pressing grid operators to answer for 3 decades, is whether the upgrades implemented since 1989 are sufficient against a storm significantly larger than what March 1989 produced. Hydro spent $2 billion Canadian dollars over 6 years after 1989 hardening its grid. Dr. Emmanuel Bernabeu of PGM, the regional utility coordinating electricity across 13 U.S. states, has stated publicly that he believes would not lose power if a March 1989 class storm occurred today. That is genuine progress. But March 1989, as severe as it was, registered on the NOAA scale at what researchers now classify as approximately G for one full level below G5, the maximum. The Carrington event of September 1859 is estimated to have been roughly twice as strong as March 1989, twice a Carrington scale event striking. The modern grid, a grid far more extensive, far more interconnected, and supporting far more technology dependent on stable power than the grid of 1989, is an event for which no utility on Earth has fully modeled the cascading failure modes. A 2008 report by the Space Studies Board estimated potential damages in the trillions of dollars. The word trillions in that context is not hyperbole. It is a conservative engineering estimate. The system is not inactive. It is accumulating, and today's storm must be understood in the context of where Solar Cycle 25 stands right now. NOAA's Solar Cycle 25 Prediction Panel, a body convened by NOAA, NASA, and the International Space Environmental Services, predicted that Cycle 25 would reach a maximum sunspot number of 115, with the peak occurring between November 2024 and March 2026. The solar cycle maximum, the period of most intense solar activity, has either just passed or is passing right now, and here is what the solar cycle's descending phase means that most people do not realize. The declining phase of a solar cycle does not immediately become quiet. The Solar Terrestrial Center of Excellence, the SEI, in Brussels, maintains detailed tracking of Solar Cycle 25 and notes that the highest monthly geomagnetic AP index values, the index measuring geomagnetic disturbance, almost always occur to 2 for years after solar maximum. 4 years after a cycle peak that occurred somewhere in the window of 2025 to early 2026 means the period of greatest geomagnetic storm frequency may still be ahead. The reason is specific: equatorial coronal holes, the type of coronal hole responsible for today's storm, maximize in number and in geoeffectiveness. During the declining phase of the solar cycle, the sun, moving past its peak, begins to open more equatorial holes. Each one launches a high-speed wind stream. Each stream produces a correlating interaction region. Each CIR can drive G1 to G2 geomagnetic storms with a reliability that distinguishes them from coronal mass ejections because, unlike CMEs, CIRs are predictable days in advance, and they recur on the sun's approximately 27-day rotation cycle. The same coronal hole responsible for today's G2 storm will rotate back into an Earth-facing position roughly 27 days from now. The system is not a one-time event, it is a recurring cycle. Space weather researchers treat the next 18 months as a window of elevated systemic risk for satellite infrastructure and high-latitude power grids, according to reporting from Tech Times drawing on solar cycle progression data. That framing elevated systemic risk is the language of people who have looked carefully at the data and chosen not to minimize what it shows. Scientists choose their language carefully here, and that careful language is itself the warning. The SEI notes that Solar Cycle 25 has already set records within the cycle for the smoothed AP geomagnetic index. The highest smoothed value measured in Solar Cycle 25 for the AP index reached 1564 nanotesla as of August 2025, a cycle high, and SEI forecasters project that the AP values are expected to increase further in the months ahead, driven by the enhanced geomagnetic activity observed in late 2025 and early 2026. More disturbance, not less. The trend is upward. Now return to the people living in the path of this. Not in Churchill, Manitoba, this time, but in Troms, Norway, a city of approximately 77,000 people situated at nearly 70 degrees north latitude, well inside the Arctic Circle, and fully within the zone where G2 storm effects on power infrastructure are considered not merely possible but expected during active conditions. Troms is a remarkable city. It has a university. It has a cathedral. It has a thriving cultural scene built on the fact that it is far enough north to see the aurora borealis regularly, which draws tourists from around the world. It is also a city in which heating is not a comfort, it is a survival requirement. Winter in Troms brings polar night, months in which the sun does not rise above the horizon at all. The temperature regularly drops to minus 15 Celsius or colder. If you ask someone in Troms tonight what a geomagnetic storm means for their life, the honest answer is, it depends entirely on the magnitude of the storm and the preparation of the grid. A G2 storm, well managed, means the lights might flicker and the aurora might be spectacular. A G4 or G5 storm, on infrastructure that has not been hardened to handle sustained geomagnetically induced currents in the kilowatt range, means something that no responsible space weather communicator should leave unsaid. It means that the power could go off in the middle of a polar night in a city at 70 degrees north. In temperatures that kill within hours of unprotected exposure. This is not a hypothesis. This is documented in the geological record and in the engineering record both. The 2003 Halloween storms classified at G4 and G5 caused a power blackout in Malmö, Sweden, leaving 50,000 people without electricity. The same storm cluster induced currents in the Finnish natural gas pipeline network and caused transformer damage in South Africa. In China, the currents produced vibration and noise in transformers at the Sheng substation and at the Lingo nuclear power plant. These were not marginal effects at extreme latitudes. They were infrastructure impacts across multiple continents at multiple latitudes from a single sequence of solar storms. And the 2003 Halloween storms, severe as they were, did not achieve the full destructive potential of a Carrington-scale event, not close. The connected systems extend further still. Today's geomagnetic storm is also interacting with Earth's radiation belts, the Van Allen belts, two concentric zones of energetic charged particles trapped in Earth's magnetic field. During G2 conditions, the ring current, the belt of energetic particles encircling Earth at distances of roughly 2 to 9 Earth-rad intensifies. It was precisely to study this intensification in real time that NASA and the U.S. Space Force launched the STORY instrument aboard the ISS, reported by Tech Times on May 15, 2026. STORY, the Storm Time O+ Ring Current Imaging Evolution instrument, is now mounted on the exterior of the ISS's Columbus module, scanning the ring current during this exact storm period. Its core scientific question is foundational. Are the energetic particles feeding the ring current sourced from the solar wind or from Earth's own upper atmosphere? The answer determines how future models predict storm intensity and therefore how much warning infrastructure operators can be given before a major event. The fact that this instrument is operating right now during today's G2 storm is not coincidence. It is the intersection of solar cycle timing and scientific preparation. The monitoring is in place, detection is possible, prediction remains probabilistic, not certain, and that gap between detection and certainty is where millions of people live. The broader connection between today's solar wind event and the health of Earth's ionosphere is equally direct and equally consequential. The ionosphere is the electrically charged layer of Earth's upper atmosphere, beginning at approximately 60 kilometers altitude and extending to around 1,000 kilometers. It is the layer through which HF radio signals propagate by reflecting off charged particles, allowing signals to travel far beyond the horizon, across oceans, over continents. During G2 geomagnetic storms, the ionosphere becomes turbulent. Charged particle flows from the magnetosphere inject energy into the polar ionosphere, creating density irregularities that scatter and absorb radio signals. Transpolar aviation routes, the great circle paths flown by aircraft between North America and Asia over the Arctic, depend on HF radio as a primary communication band at those latitudes where satellite coverage is limited. During today's storm, those routes face exactly the communication degradation that NOAA's G2 scale formally documents. Weak to minor HF degradation on the sunlit side, with the potential for occasional complete loss of radio contact. Airlines monitoring this event have the option to divert to lower latitude flight paths. That option costs time and fuel. When the storm is G2, most operators accept the risk and continue. The question space weather researchers ask is, what is the contingency plan when the storm escalates and the ionosphere no longer reflects, it absorbs? Minutes are not hours, and in this context, that difference is everything. The speed with which the March 1989 hydro grid collapsed 90 seconds from onset to full transmission failure is the number that engineers return to when they model geomagnetic risk. Not 90 minutes, not 90 hours, 90 seconds. The grid did not fail slowly, giving operators time to isolate sections, reduce loads, protect transformers. It failed in a cascade so rapid that the protective relay systems that tripped systems designed to prevent damage contributed to the cascade by disconnecting load faster than operators could compensate. The system's own defenses became part of the failure mode. The research published by Bottler in 2019 in Spaceweather journal is specific. The second storm's sudden commencement, arriving at 7:43 UTC, coincided with a substorm that externally triggered the geomagnetically induced currents beyond what the system could absorb. External triggering, the compounding of two separate solar events interacting with each other at Earth's magnetosphere, accelerated the onset. The grid did not fail because operators were unprepared. It failed because the physics moved faster than any operator response could. Today's storm is G2. Today's storm is not 1989. But the CI driving today's event, according to NOAA's Watchers News reporting on May 14th, was accompanied by the lingering effects of the M5-8 class CME from active region 4436 that launched on May 10th. Multiple drivers, overlapping impacts. The CIR and the fading CME influence arrived at Earth in sequence, not in isolation. This is not the same as March 1989, but the structural pattern of compounding solar influences driving geomagnetic conditions is identical in type, even if different in magnitude. And the solar cycle's declining phase, which is now beginning, is the phase in which equatorial coronal holes recur with increasing frequency. Every 27 days, approximately, the same breach in the sun's magnetic atmosphere rotates back. Every 27 days, forecasters at NOAA's Space Weather Prediction Center issue new watches. Every 27 days, grid operators at high latitudes assess the situation and decide whether to implement precautionary load management. The risk does not end when today's storm subsides. The forecast for May 2026 already carries a second notable geomagnetic storm period projected for approximately May 23 to 27, two storm windows in 1 month, both driven by the same mechanism: coronal holes on a sun that is entering its most geo-effectively active phase. The 7 cm solar radio flux, the standard measurement of overall solar activity, measured daily at the Dominion Radio Astrophysical Observatory in Penticton, British Columbia, stood at 106 solar flux units on May 15, 2026, according to spaceweather. COM data updated that date. That number represents a moderately elevated level of solar output. The solar disk on May 14 carried 4 active regions, with region 4435 showing growth and producing a C5 flare peaking at 642 UTC. C-class flares are the smallest category of significant solar eruption, but active regions grow, sunspot groups evolve. A beta-class active region, one with a simple bipolar magnetic structure, can become a beta-gamma-delta in a matter of hours, placing it in the class from which X-class flares, the most powerful category, originate. The current solar environment is not quiescent, it is not declining rapidly, the thermosphere, Earth's outermost atmospheric layer, registered a climate index value of 16.48 times 10 to the 10th watts on May 15, indicating elevated solar heating from the present solar wind environment. The thermosphere is expanding, satellites in low Earth orbit are experiencing drag, their operators are compensating. The system is not passive, it is responding in real time to inputs that began with a gap in the sun's atmosphere detected days ago by a satellite instrument in extreme ultraviolet. Consider what it means that all of this, the coronal hole, the solar wind, the CIR, the magnetospheric compression, the geomagnetically induced currents flowing through continental geology, the ionospheric turbulence disrupting aviation radio, the ring current swelling around Earth, was set in motion not by a violent solar explosion, but by an absence. A coronal hole is not an eruption. It is not a flare. It is a place where the sun's magnetic field opens outward instead of looping back on itself, and where the solar atmosphere is thinner, darker, cooler, and allows the solar wind to escape faster and more directly into interplanetary space. It is emptiness in the sun's atmosphere that drives the storm. It is the hole, not the explosion, that presses at 700 kilometers per second against the shield that protects everything we have built. And here is the fact with which to end. NOAA's 5-tier storm scale runs from G1 to G5. Every G5 event in documented history began at G1. The Carrington event of September 1859, the most powerful geomagnetic storm in recorded human history, a storm that set telegraph wires on fire across Europe and North America from the induced currents alone, a storm that was observed as auroras as far from the poles as Cuba and Colombia, began as a solar disturbance that no observer alive at the time could have identified, on a star that had been doing precisely this, cycling through its activity, opening its holes, launching its winds, and pressing its invisible electromagnetic force against this planet for approximately 4.6 billion years before a single human instrument existed to detect it.